Settle in, find comfort, and let your mind drift. Welcome to Sleep Science Stories. Tonight, we begin a journey that stretches across the vast, silent sea of space, aboard the tiny, yet monumental, vessel, Voyager 1. Its story began right here, on our own planet. In the summer of 1977, all people danced to disco and looked up at a sky filled with familiar constellations. Humanity prepared to send a message in a bottle into the cosmic ocean. The world was different then, simpler in some ways, more uncertain in others. But in that summer, something extraordinary was taking shape at Cape Canaveral, Florida. On September 5th of that year, Voyager 1 lifted off, carried aloft by a Titan III rocket, rising on a column of fire into the blue. It was the second of the twin Voyager spacecraft to launch, though. Paradoxically, it would become the first to reach the outer planets, overtaking its sibling on a faster trajectory through the solar system. Close your eyes now, and picture this spacecraft. The vessel itself is remarkably modest in size for something carrying humanity's hopes into the infinite dark. Weighing just 825 kilograms, about the same as a small car. Voyager 1 measures roughly 3.7 meters across. To put that in perspective, you could fit it comfortably in a standard living room. Yet from this humble frame extends a story of ambition that spans nearly 5 decades and counting. Breathe deeply, and imagine this small craft, no larger than the space you rest in now, drifting through the endless void. Every component of Voyager 1 had to be chosen with extraordinary care, each piece a testament to human ingenuity. The spacecraft carries 3 radioisotope thermoelectric generators, devices that convert heat from decaying plutonium-238 into electricity. When Voyager 1 began its journey, these generators produced about 470 watts of power. That's roughly enough to run 5 standard light bulbs. But in the eternal night of deep space, where solar panels become useless beyond Mars, this nuclear battery was the only option for a mission expected to last decades. Even now, as you rest here, that gentle power source continues its work, billions of miles away, a warm heartbeat in the cold. The timing of the launch was no accident, but rather a rare gift from the heavens themselves. Scientists had identified a celestial alignment, one that occurs only once every 176 years. The outer planets would arrange themselves in such a way that a spacecraft could use the gravity of one planet to slingshot itself toward the next, like a stone skipping across a cosmic pond. This gravitational assist technique would allow Voyager 1 to visit multiple worlds without carrying impossible amounts of fuel. The window for this grand tour was narrow, and 1977 was the year to seize it. Imagine the patience required waiting for the planets themselves to align, for nature to open a door that appears only twice in 3 human lifetimes. As Voyager 1 climbed through Earth's atmosphere and broke free from our planet's embrace, it carried with it a speed that would eventually define its legacy. The spacecraft would reach a velocity of approximately 17 kilometers per second relative to the Sun. That's more than 38,000 miles per hour. At this speed, you could travel from New York to Los Angeles in less than 4 minutes. Let that thought wash over you. Such incredible velocity, carrying this small messenger ever outward, ever faster, racing away from the only home it has ever known. But Voyager 1 wasn't just built for speed. It carried 11 scientific instruments, each designed to peel back the mysteries of worlds no human eye had ever seen up close. There were cameras to capture images in both visible and ultraviolet light, instruments to measure magnetic fields and charged particles, sensors to detect cosmic rays, and devices to study planetary atmospheres and radio emissions. Each instrument represented years of engineering ingenuity, miniaturized and hardened to survive the brutal environment of space. Each one a question asked of the universe, waiting patiently for an answer. Among all the sophisticated equipment, perhaps the most poignant payload was something decidedly low-tech. A golden phonograph record. Rest your mind on this image. This was the golden record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. The record includes greetings in 55 languages, music from different cultures and eras, and 116 images showing mathematical definitions, the solar system, DNA structure, human anatomy, and scenes from Earth. It even includes the brain waves of Intruyen, one of the record's creators, recorded as she meditated on the history of Earth and the nature of human love. The record was encased in a protective aluminum jacket, along with a cartridge, stylus, and instructions for playing it, all designed to last billions of years in interstellar space. A love letter to the cosmos, traveling on behalf of us all. The mission was given an initial planned duration that seems almost quaint in retrospect. NASA designed Voyager 1 to last for just 5 years, long enough to complete flybys of Jupiter and Saturn. The engineers built in redundancy where they could, but no one truly believed the spacecraft would still be functioning in the 21st century. Yet here we are, decades later, and Voyager 1 continues to transmit, continues to teach, continues to voyage ever outward into the dark. It has outlived its own expectations, exceeded every hope, and become something more than its creators ever imagined. As September turned to autumn in 1977, and Voyager 1 settled into its long cruise toward Jupiter, the spacecraft became a silent ambassador, carrying not just instruments and data, but humanity's hope that somewhere, someone, we might not be alone in contemplating the stars. And so it began its journey, patient and steady, into the night that would become its eternal home. The journey to Jupiter would take time, a slow ballet across the inner solar system. Voyager 1 would not reach the giant planet until March of 1979, nearly 18 months after leaving Earth. During this cruise phase, the spacecraft wasn't simply coasting through empty space. Its instruments awakened gradually, calibrating themselves, testing their sensors against the known backdrop of stars and the distant sun mission controllers. Back on Earth monitored every signal, every data packet, learning the spacecraft's rhythms and moods. Communication with Voyager 1 occurs through NASA's Deep Space Network, a collection of giant radio antennas positioned at 3 locations around Earth: Goldstone in California's Mojave Desert, near Madrid in Spain, and near Canberra in Australia. These 3 sites are spaced roughly 120 degrees apart in longitude, ensuring that as Earth rotates, at least one antenna can always maintain contact with the spacecraft. The antennas are massive structures, their primary dishes measuring 70 meters across, large enough to capture the faint whisper of Voyager's signal from billions of kilometers away. That signal is extraordinarily weak by the time it reaches Earth. Voyager 1 transmits with a power of just 23 watts, about the same as a refrigerator light bulb. By the time this signal traverses the vast emptiness of space, it arrives at Earth with a strength of about 20 billion times weaker than the power needed to run a digital watch. Yet the Deep Space Network's sensitive receivers can detect this ghostly transmission and decode the precious data within. The spacecraft's main antenna, a 3.7-meter high-gain dish, must be precisely pointed at Earth to maintain communication. This dish is Voyager's lifeline, its voice across the void. If the antenna drifts even slightly off target, the signal is lost. To keep it aligned, Voyager 1 uses celestial navigation, locking onto the Sun and the bright star Canopus as reference points. Small thrusters fire in carefully calculated pulses to adjust the spacecraft's orientation, maintaining that tenuous thread connecting it to home. As Voyager 1 approached Jupiter in early 1979, the mission team faced a challenge unlike anything encountered in previous planetary missions. Jupiter's radiation environment is ferocious, with trapped particles in its magnetosphere creating radiation levels that could fright unprotected electronics in minutes. The spacecraft had been designed with this hazard in mind, its sensitive components shielded behind layers of protective material. Still, there are no guarantees. Voyager 1 would be venturing into a maelstrom of high-energy particles, and the team could only watch and hope their preparations had been sufficient. The encounter with Jupiter began with distant observations in January 1979, but the closest approach came on March 5, when Voyager 1 swept past the giant planet at a distance of just 278,000 kilometers from its cloud tops. To put this in perspective, that's closer than the distance from Earth to our moon. For a spacecraft traveling at such tremendous velocity, this close approach represented a brief but intense period of observation. Every instrument strained to capture as much data as possible during those precious hours. What Voyager 1 revealed transformed our understanding of Jupiter. The spacecraft's cameras captured images of unprecedented clarity, showing the intricate structure of Jupiter's cloud bands, the roiling chaos of its great red spot, and atmospheric features never before seen. But perhaps more surprising were the discoveries that couldn't be predicted from Earth-based observations. Voyager 1 found that Jupiter has a faint ring system, gossamer threads of dust particles orbiting the planet's equator. Until that moment, only Saturn was known to possess rings. The discovery suggested that ring systems might be far more common in the solar system than anyone had imagined. The volcanic activity on Jupiter's moon Io stands as one of Voyager 1's most astonishing discoveries. As the spacecraft's cameras turned toward the sulfur-colored moon, navigation engineer Linda Morabito was examining images intended for optical navigation when she noticed something peculiar, a strange umbrella-shaped feature extending above Io's limb. It took a moment to comprehend what she was seeing. The feature was a volcanic plume, erupting hundreds of kilometers into space. This was the first active volcanism ever observed beyond Earth. Voyager 1 ultimately detected 8 active volcanic plumes on Io, with eruption columns reaching up to 300 kilometers high. The moon's surface, painted in yellows, oranges, and reds from sulfur compounds, was being constantly renewed by volcanic resurfacing, making it the most geologically active body in the solar system. The gravity assist from Jupiter did more than enable Voyager 1 to continue to Saturn. It also accelerated the spacecraft significantly, adding velocity that would eventually help propel it out of the solar system entirely. As Voyager 1 swung around Jupiter's immense bulk, the planet's gravity pulled the spacecraft forward in its orbit, while the spacecraft's gravity pulled infinitesimally back on Jupiter, slowing the giant planet by an amount so small it could never be measured. This exchange of momentum, this cosmic handshake, sent Voyager 1 racing onward with renewed speed toward the ring jewel of Saturn, toward destinations that existed only as points of light in the darkness ahead. The cruise from Jupiter to Saturn took another 9 months, and Voyager 1 arrived at the ring planet in November 1980. Saturn had been observed through telescopes for centuries, its magnificent ring system a source of wonder since Galileo first glimpsed it through his primitive lens in 1610. But nothing could prepare scientists for the complexity that Voyager 1 would reveal. On November 12, 1980, Voyager 1 made its closest approach to Saturn, passing within 124,000 kilometers of the planet's cloud tops. This was even closer than its approach to Jupiter, a daring trajectory that took the spacecraft through the plane of Saturn's rings and then upward, using Saturn's gravity to redirect its path toward the moon Titan. The choice of trajectory was deliberate and consequential. Mission planners had to decide, continue onward to Uranus and Neptune, or make a close flyby of Titan, Saturn's largest moon. They chose Titan, a decision that would ultimately send Voyager 1 on a path out of the ecliptic plane, away from the other outer planets, but towards something equally profound. Titan had long intrigued scientists because spectroscopic observations from Earth suggested it possessed a thick atmosphere, something rare among moons. Voyager 1's close approach to Titan on November 11, 1980, confirmed that this moon has an atmosphere denser than Earth's, with a surface pressure about 1.5 times that of our own planet. The primary component is nitrogen, just like Earth's atmosphere, but Titan's air also contains methane and other hydrocarbons, giving it an orange haze that completely obscures the surface from visible light. The spacecraft's instruments detected complex organic chemistry occurring in Titan's upper atmosphere, where ultraviolet light from the distant sun breaks apart methane molecules, allowing them to recombine into more complex compounds. In many ways, Titan's atmosphere resembles what Earth's might have been like billions of years ago, before life transformed our world. The images Voyager 1 sent back from Saturn's rings were nothing short of revelatory. What had appeared from Earth as a handful of distinct rings resulted into thousands upon thousands of individual ringlets, like grooves on a cosmic phonograph record. The rings showed elaborate structure, gaps, waves, braids, and spokes, dark radial features that rotated with the rings like ghostly shadows. Scientists realized they were witnessing gravitational choreography of extraordinary subtlety, with shepherd moons sculpting ring edges, resonances creating gaps, and small moonlets embedded within the rings themselves, carving out spaces in the icy debris. Voyager 1 discovered several new moons orbiting Saturn, adding to the retinue of worlds in the Saturnian system. These small bodies, some irregular in shape, some smooth and icy, orbit among the rings or in the spaces between them. Each discovery added another piece to the puzzle of how this magnificent system formed and evolved. The total count of Saturnian moons known at the time increased significantly, though future missions and observations would eventually push that number far higher. The spacecraft's observations of Saturn itself revealed a world of subtle beauty. Unlike Jupiter's bold bands and swirling storms, Saturn's atmosphere appeared more muted, with pastel yellows and golds blending into each other. But beneath this calm appearance, Voyager 1's instruments detected powerful winds, with velocities near the equator reaching up to 1,800 kilometers per hour, faster than any winds on Jupiter and among the fastest in the solar system. The planet's famous hexagonal cloud pattern at its north pole, though better documented by later missions, was glimpsed in Voyager's data, a geometric mystery that persists to this day. After the Saturn encounter, Voyager 1's planetary mission was complete. The spacecraft had fulfilled its primary objectives, visiting 2 giant planets and their moons, returning thousands of images and volumes of scientific data that would take years to fully analyze. But the spacecraft was still healthy, still functioning, still speeding outward. The decision was made to continue the mission into a new phase, one without a specific destination, but with a profound purpose: to explore the boundary between the Sun's influence and interstellar space. As Voyager 1 climbed away from the ecliptic plane, that flat disk where most planets orbit, it began a journey perpendicular to the solar system's main plane. The spacecraft was now heading roughly toward the constellation Ophiuchus, moving away from the Sun at about 3.6 astronomical units per year. An astronomical unit is the distance from Earth to the Sun, roughly 150 million kilometers. So Voyager 1 was receding at a rate of about 540 million kilometers per year, though in the cosmic scheme of distances, this was still a patient crawl. The spacecraft's plutonium power source continued to decay, as it inevitably must. The generators were losing about 4 watts of power each year, a slow but steady decline that mission engineers had to account for in every decision. With less power available, choices had to be made about which instruments to keep running and which to power down. Each instrument shut down was a small farewell, a recognition that Voyager 1's capabilities, while still impressive, were gradually diminishing as it ventured ever deeper into the cold and dark. In February 1990, Voyager 1 reached a significant milestone in its journey. At a distance of about 6 billion kilometers from Earth, more than 40 times farther from the Sun than our planet, the spacecraft turned its cameras back toward home one final time. This maneuver was suggested by astronomer Carl Sagan, who had been deeply involved with the Voyager mission from its inception. He understood that this would be the last opportunity to capture images of the solar system from such a distant vantage point before the cameras were shut down forever to conserve power. The resulting images became known as the family portrait of the solar system. Voyager 1 captured 60 frames showing 6 of the solar system's planets: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. Mercury was too close to the Sun's glare to photograph, and Mars was lost in scattered sunlight. But Earth appeared, and in that photograph lies one of the most humbling images ever captured. Earth, in that image, occupies less than a single pixel, a pale blue dot suspended in a sunbeam, a consequence of scattered light in the camera's optics. The photograph shows our entire world, every person who has ever lived, every civilization that has risen and fallen, every joy and sorrow, contained in that tiny point of light measuring just 0.12 pixels in size. From 6 billion kilometers away, Earth has no special significance. It is simply one small world among others, a mote of dust floating in an endless cosmic arena. After taking the family portrait, Voyager 1's imaging system was powered down permanently on February 14, 1990. The cameras had served their purpose magnificently, capturing nearly 19,000 images of Jupiter and its moons, and more than 18,000 images of Saturn and its system. But with no more planets to photograph and power becoming increasingly precious, the decision was made to shut down the cameras and preserve electricity for other instruments that could continue gathering data about the outer reaches of the solar system and beyond. The mission entered what NASA called the Voyager Interstellar Mission, or VIM. The primary goal shifted from planetary exploration to studying the outer boundaries of the Sun's influence. The heliosphere, the bubble of charged particles blown outward by the solar wind, extends far beyond the planets, but it doesn't extend forever. Somewhere in the distant dark, the solar wind must slow, must stop, must give way to the interstellar medium, the thin gas that fills the space between stars. Voyager 1 was heading toward that boundary, though no one knew exactly where it lay. Throughout the 1990s and into the 2000s, Voyager 1 continued its outward journey, now traveling through a region where the solar wind still dominated but was beginning to feel the pressure of interstellar space. The spacecraft's instruments measured variations in cosmic rays, solar wind particles, and magnetic fields, building a picture of this poorly understood realm. Mission scientists watched the data carefully, looking for signs that Voyager 1 was approaching something significant. In December 2004, at a distance of about 94 astronomical units from the Sun, Voyager 1 crossed what scientists call the termination shock, the boundary where the solar wind abruptly slows from supersonic to subsonic speeds. Here, the outward rushing solar wind collides with the pressure of the interstellar medium, creating a shock wave much like the bow wave that forms when a boat moves through water. Voyager 1's instruments detected a sudden increase in the density and temperature of the solar wind, confirming that it had passed through this invisible boundary. The spacecraft was now in a region called the heliosheath, a turbulent zone between the termination shock and the heliopause itself. The journey through the heliosheath took years. This region proved to be far more complex than anticipated, with the magnetic field taking on unexpected orientations and cosmic rays from interstellar space beginning to penetrate in greater numbers. Voyager 1's instruments, designed decades earlier for a 5-year mission, continued to function and report back, sending their faint signals across a distance that now took light itself more than 13 hours to traverse. Communication with Voyager 1 had become an exercise in patience. A command sent from Earth would take over 13 hours to reach the spacecraft. Voyager 1's response would take another 13 hours to return. Any interaction with the spacecraft now involved more than a day of waiting, a conversation conducted at the speed of light across a gulf of emptiness that staggered the imagination. Yet that conversation continued, a testament to both the robustness of 1970s engineering and the dedication of the mission team who had tended this spacecraft for decades. By 2010, Voyager 1 had traveled farther from the Sun than any other human-made object, a record it continues to hold. The spacecraft had surpassed the previous record holder, Pioneer 10, which had fallen silent in 2003. Now Voyager 1 stood alone at the frontier, the most distant envoy of human civilization, pushing ever deeper into unexplored territory. As the spacecraft ventured through the heliosheath, scientists began to notice something remarkable in the data. The intensity of galactic cosmic rays, high-energy particles that originate outside our solar system, was steadily increasing. These particles, accelerated by distant supernovae and other violent cosmic events, are partially blocked by the solar wind and the Sun's magnetic field. But as Voyager 1 moved outward, the shielding effect weakened, and more cosmic rays reached the spacecraft's detectors. This was a signpost on the road to interstellar space, an indication that the sun's protective bubble was thinning. In the spring of 2012, readings from Voyager 1's instruments began to change more dramatically. The intensity of lower-energy solar particles started to drop while cosmic ray levels continued to rise. Something was shifting in the environment around the spacecraft. Scientists debated what these changes meant. Was Voyager 1 approaching the heliopause, the true boundary of the solar system? Or was this merely another transition within the heliosheath, a false alarm in a region that had already proven full of surprises? Then, on August 25, 2012, though the significance wouldn't be confirmed until later, Voyager 1 crossed the heliopause. At a distance of approximately 122 astronomical units from the Sun, more than 18 billion kilometers, the spacecraft slipped across an invisible threshold and entered interstellar space. It had taken 35 years to reach this boundary, but Voyager 1 had finally left the solar system's protective embrace and entered the realm between the stars. The crossing wasn't immediately obvious. Voyager 1's magnetometer had failed years earlier, so the spacecraft couldn't directly measure changes in the magnetic field that would have clearly marked the transition. Instead, scientists had to rely on indirect evidence. It wasn't until 2013, when they analyzed a fortuitous detection of plasma oscillations, ripples in the surrounding charged gas triggered by a solar eruption, that they could definitively calculate when and where the crossing had occurred. The density of plasma in interstellar space is about 40 times higher than in the outer heliosheath, and these oscillations revealed that Voyager 1 was indeed in a new environment. With this achievement, Voyager 1 became the first human-made object to enter interstellar space. The term requires some nuance. The spacecraft hadn't left the Sun's gravitational influence, which extends much farther, perhaps a light-year or more. The Oort cloud, a vast spherical shell of icy bodies that marks the outer edge of the Sun's gravitational domain, likely extends halfway to the nearest stars. Voyager 1 would need tens of thousands of years to traverse this region. But in terms of the solar wind and the Sun's magnetic field, the spacecraft had indeed departed the heliosphere and entered the space between stars. The temperature in interstellar space is different from what Voyager 1 experienced within the heliosphere. The interstellar medium has a temperature of about 15,000 Kelvin, far hotter than the few tens of thousands of degrees in the heliosheath. This seems paradoxical. How can interstellar space be hot when we think of space as cold? The answer lies in the difference between temperature and heat. Temperature measures the average kinetic energy of particles, but in the near-perfect vacuum of space, there are so few particles that they carry almost no actual thermal energy. A thermometer in interstellar space would still freeze, despite the high temperature of the sparse gas around it. In interstellar space, Voyager 1 continues to measure cosmic rays, plasma waves, and the magnetic field, slowly building a picture of this new realm. The data reveals that interstellar space is not uniform or empty. There are subtle variations in density and temperature, magnetic fields that thread through the galaxy, and particle populations that speak to processes occurring far away. Every measurement Voyager 1 sends back is a first, a glimpse of a region that no spacecraft had ever sampled before. As the years pass, Voyager 1 continues its journey through this uncharted ocean. The spacecraft is currently moving at about 17 kilometers per second relative to the Sun, but in the reference frame of the local interstellar medium, its velocity is different, affected by the Sun's own motion through the galaxy and the motion of nearby gas clouds. In approximately 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445, currently a dim red dwarf in the constellation Camelopardalis. The spacecraft will drift silently past, an artifact from a distant world, still carrying its golden record, still bearing the message that humanity once looked up at the stars and wondered. The management of Voyager 1 and its extended mission requires constant vigilance and creative problem-solving. The spacecraft was never designed to operate for nearly 5 decades, yet here it continues, a testament to over-engineering and careful stewardship. The mission team, based at NASA's Jet Propulsion Laboratory in Pasadena, California, includes engineers who have worked on Voyager since the beginning, alongside younger team members who weren't even born when the spacecraft launched. Together, they navigate the challenges of maintaining a probe that runs on technology from the 1970s. One of the most critical challenges is managing the declining power supply. As of recent years, Voyager 1's 3 radioisotope thermoelectric generators produce approximately 249 watts of power, down from the original 470 watts at launch. This steady decline means difficult decisions must be made regularly about which systems to keep operational. The team has developed innovative solutions, including turning off heaters for instruments and allowing them to operate at temperatures far below their original design specifications. Remarkably, many instruments continue to function even when operating at temperatures their designers never imagined they could survive. In November 2023, Voyager 1 experienced a communications anomaly that sent the mission team into high alert. The spacecraft's flight data system began sending garbled data back to Earth instead of the usual telemetry. For months, engineers worked to diagnose the problem from 15 billion miles away, sending commands and waiting over a day for responses. They eventually traced the issue to a corrupted memory chip in the flight data system, likely damaged by cosmic radiation or simply worn out after decades of operation. The solution required something extraordinary, reprogramming code that hadn't been modified in decades, spreading it across different locations in the spacecraft's ancient memory to work around the failed chip. In April 2024, after months of painstaking work, the team successfully restored Voyager 1's ability to send back scientific data. The spacecraft, built with 1970s computer technology that has less processing power than a modern calculator, had been coaxed back to life through the ingenuity of engineers working with systems designed nearly half a century ago. Voyager 1's data storage is incredibly limited by modern standards. The spacecraft's onboard tape recorder, used to store data when the spacecraft wasn't in communication with Earth, has long since been turned off. The digital data system that processes instrument readings operates with a memory capacity measured in kilobytes, not gigabytes or terabytes. Yet this modest computational power has been sufficient for the spacecraft's needs, a reminder that sophisticated science doesn't always require sophisticated computers. The attitude control system, which keeps Voyager 1 properly oriented, relies on thrusters that fire brief pulses to adjust the spacecraft's pointing. These trajectory correction maneuver thrusters were originally intended for course corrections during the planetary encounters. After decades of disuse, engineers successfully tested them in 2017, finding that they still functioned, though they required a warming period due to the spacecraft's declining power and internal temperatures. In 2023, the team switched to a different set of thrusters to conserve fuel and maintain the spacecraft's orientation toward Earth. The spacecraft travels through a realm so empty that it's difficult to comprehend. The density of the interstellar medium that surrounds Voyager 1 is approximately 1 atom per cubic centimeter. For comparison, Earth's atmosphere at sea level contains about 10 to the power of 19 molecules per cubic centimeter. If you could take a cubic meter of the space around Voyager 1 and compress it to Earth's atmospheric pressure, it would occupy a volume smaller than a single atom. This is emptiness beyond any earthly vacuum, a void punctuated only by the occasional atom of hydrogen or helium, and rare cosmic ray particles screaming through at relativistic speeds. Despite the extreme emptiness, Voyager 1's instruments can still detect structure in the interstellar medium. The spacecraft has measured variations in the magnetic field orientation, detected boundaries between different regions of interstellar space, and observed how galactic cosmic ray intensities change over time. These measurements suggest that interstellar space has its own weather, its own dynamics, shaped by the motion of nearby stars, the pressure of starlight, and the remnants of ancient supernova explosions. The spacecraft's journey is far from over, even as its power continues to wane. Scientists estimate that Voyager 1 will have sufficient power to operate at least one scientific instrument until approximately 2025, with the possibility of extending operations into the early 2030s depending on power management decisions. After that, the spacecraft will fall silent, but it will continue to coast through space, a monument to human curiosity, drifting through the galaxy long after the civilization that built it has become dust. The scientific legacy of Voyager 1 extends far beyond its initial planetary encounters. The mission fundamentally transformed our understanding of the outer solar system, revealing worlds of unexpected complexity and beauty. Before Voyager, Jupiter and Saturn were known largely through telescopic observations that showed only the largest features. Voyager 1 revealed these worlds in intimate detail: the intricate turbulence of Jupiter's atmosphere, the delicate braiding of Saturn's rings, the surprising volcanism of Io, the dense atmosphere of Titan. Each discovery opened new questions, inspired new missions, and reshaped entire fields of planetary science. The influence of Voyager 1 can be seen in subsequent missions to the outer solar system. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, built upon Voyager's discoveries, studying the Jovian system in far greater detail. The Cassini mission to Saturn, which operated from 2004 to 2017, was conceived in part because of the tantalizing glimpses Voyager provided of Saturn's moons and rings. Even the New Horizons mission to Pluto, launched in 2006, carries forward the spirit of exploration that Voyager embodied, pushing outward to worlds unknown, driven by curiosity and the desire to see what lies beyond the next horizon. The Voyager program as a whole, including both Voyager 1 and its twin Voyager 2, represented a remarkably cost-effective investment in scientific discovery. The total cost of building, launching, and operating both spacecraft through their primary missions was approximately $865 million in 1970s currency. Adjusted for inflation and considering the decades of extended mission operations, this represents an extraordinary return on investment for planetary encounters, dozens of moon flybys, the first entry into interstellar space, and thousands of scientific papers published from the data. One of the most poignant aspects of Voyager 1's story is the human element woven throughout. The scientists, engineers, and mission planners who designed and launched Voyager 1 did so knowing they were creating something that would outlive them. Many of those original team members have since passed away, their life's work now billions of miles from Earth, still functioning, still exploring. The mission has become a multi-generational endeavor, with knowledge and expertise passed from one cohort of engineers to the next, maintaining an unbroken thread of human care and attention stretching back to 1977. The spacecraft carries with it traces of the era that built it. The Golden Record, curated by a committee that included Carl Sagan, Andrew Timothy Ferris, and others, reflects the hopes and anxieties of the late 1970s. The selection of music includes Bach and Beethoven, Chuck Berry and Blind Willie Johnson, traditional songs from Peru, Zaire, Java, and other corners of the world. The greetings, spoken in languages from Akkadian to Wu, represent an attempt to encompass the diversity of human speech. The images show anatomy, architecture, landscapes, and scientific diagrams, a crash course in humanity for any being that might one day intercept this wandering ambassador. The probability of the golden record ever being found by an extraterrestrial civilization is vanishingly small. Space is vast beyond comprehension, and Voyager 1, for all its distance from Earth, has barely begun to cross the gulf between stars. The record was never really meant to be found. It was meant to be made, a statement to ourselves about who we are and what we value. In Andrian's words, it represents a mark of respect for the cosmos, an acknowledgement that we are part of something far larger than ourselves. As Voyager 1 moves through interstellar space, it travels through a region shaped by our sun's past. The local interstellar cloud, sometimes called the local fluff, is a region of slightly higher density within the surrounding interstellar medium. This cloud is thought to be the remnant of ancient supernova explosions, the scattered remains of massive stars that died millions of years ago. The Sun entered this cloud within the last few thousand years, and will exit it in another few thousand. Voyager 1 samples this cosmic history with every measurement, reading the story of stars long dead and the particles and fields around it. The orientation of Voyager 1 relative to the galaxy is precisely known. The spacecraft is traveling at an angle of about 35 degrees above the plane of the ecliptic, moving roughly in the direction of the constellation Ophiuchus. In galactic terms, it's heading generally in the direction of the galactic center, though at its current speed it would take hundreds of millions of years to travel even a small fraction of the distance to the Milky Way's core. The spacecraft is, in every practical sense, committed to remaining in the Sun's neighborhood, orbiting the galactic center along with our star for eons to come. The silence that will eventually descend upon Voyager 1 when its power finally fails is not quite a death. The spacecraft will continue to exist, continue to move, continue to carry its record and its instruments through the void. It will become an artifact, a time capsule, a message in a bottle set adrift in an ocean larger than any ocean of water. Future civilizations, whether human or otherwise, might one day recover it, might read its record, might wonder at the beings who built it and sent it on its eternal voyage. Or it might drift forever, unnoticed and alone, a monument to a moment when one species on one world looked up and reached out to touch the stars. The story of Voyager 1 is, in many ways, a story about time itself. The spacecraft has now been traveling for over 47 years, longer than many human lifetimes. Children who were born the day Voyager launched are now approaching their 50s, living their lives on Earth while this machine continues its patient journey through the dark. The mission has outlasted governments, outlasted technologies, outlasted the careers of everyone who worked on it. Yet it persists, a testament to something deeper than any individual life, the human drive to explore, to question, to reach beyond what we know. Every day, Voyager 1 travels approximately 1.5 million kilometers farther from Earth. That's about 4 times the distance from the Earth to the Moon, covered in just 24 hours. The numbers become almost meaningless at this scale, too large to truly grasp. But the journey continues, kilometer after kilometer, day after day, year after year, an accumulation of distance that has carried Voyager 1 farther than any other object humanity has ever created. The spacecraft's trajectory will eventually carry it through the Oort cloud, that vast shell of icy bodies that surrounds the solar system like a distant halo. This region, proposed by astronomer Jan Oort in 1950, extends perhaps a light-year or more from the Sun, marking the true edge of our star's gravitational domain. Voyager 1 will take approximately 300 years just to reach the inner edge of the Oort cloud, and another 30,000 years to pass through it entirely. These are timescales that dwarf human civilization, spans of time in which languages will be born and die, in which the face of the Earth will change beyond recognition. The cosmic rays that Voyager 1 measures in interstellar space carry information about some of the most violent events in the universe. These particles, accelerated to nearly the speed of light by supernova shock waves and other extreme phenomena, have traveled for millions or even billions of years before encountering Voyager's detectors. Some of these particles may have originated in galaxies beyond our own, making them the most distant objects Voyager 1 has ever touched, in a sense far more distant than any planet or moon. In its journey through space, Voyager 1 experiences time slightly differently than we do on Earth. Due to the effects of relativity, time passes more slowly for the spacecraft as it moves at its tremendous velocity. The difference is infinitesimal over the entire mission. Voyager 1's clocks have fallen behind Earth clocks by only fractions of a second. But it's there nonetheless, a reminder that time itself is not absolute, that it bends and flows according to motion and gravity, that even the simple act of measuring when something happened depends on where you are and how fast you're moving. The Voyager 1 mission has generated an immense archive of data, stored in various formats over the decades. The earliest data was recorded on magnetic tape, later transcribed to other media as technology evolved. Tens of thousands of images, millions of measurements, all carefully preserved and catalogued. This archive continues to yield new insights even now, as scientists return to old data with new questions and new analytical techniques. Discoveries are still being made from observations Voyager 1 made decades ago, patterns that weren't apparent at the time but become clear with the perspective of years. The spacecraft's final fate, millions or billions of years from now, is impossible to predict with certainty. It might eventually be captured by the gravity of another star, going into orbit around a sun it never intended to visit. It might collide with a planet or moon, ending its journey in a brief flash of heat and light. Or it might wander the galaxy indefinitely, drifting between stars until the universe itself grows old and cold, until the last stars burn out and space becomes truly dark and empty. But that is a concern for the distant future, for times beyond imagining. For now, Voyager 1 continues its quiet work, measuring and transmitting, speaking across the void in its faint radio whisper. The mission team listens, interprets, and publishes, adding line by line to humanity's understanding of the cosmos. It is patient work, careful work, work that requires dedication across generations. And so Voyager 1 travels on through the infinite night, carrying its golden disk of songs and voices, its cargo of human hope and wonder. It moves through a darkness lit only by stars, past clouds of gas glowing faintly in starlight, through magnetic fields that curve and flow in patterns shaped by galactic forces beyond our full understanding. It is alone out there, farther from home than any messenger has ever been, yet connected still by that thread of radio waves, that conversation across the light hours that says, "We are here, we remember you, you are not forgotten." Sleep now, and dream of that small craft among the stars. Dream of its long journey through the dark, of the worlds it has seen, of the boundary it crossed into the realm between suns. Dream of the patient engineers who tend it still, sending their commands and listening for replies across the vast and patient void. Dream of the golden record spinning in silence, waiting through eons for ears that may never hear it, yet precious nonetheless. Voyager 1 continues its voyage tonight, as it has every night since 1977, moving ever outward, ever farther into the cosmic ocean. And in its journey, it carries a piece of us all, our curiosity, our dreams, our hope that the universe might be understood, that the darkness might be illuminated, that we might find our place among the stars. Rest well, knowing that even now, something we created is out there, exploring on our behalf, reaching toward mysteries we may never live to solve. Let that thought comfort you as you drift into sleep, as peaceful as the long silence of space, as deep as the darkness between the stars. Good night, and sweet dreams.